Hi everyone! Today, we're diving into a fascinating challenge, solving Sudoku. We'll explore how to tackle this popular puzzle using a powerful programming technique called backtracking. This isn't just about finding the answer, it's about understanding the logic behind a robust algorithmic approach and how it translates into code. Sudoku puzzles are simple to understand. You have a 9 by 9 grid. Some cells are already filled with numbers. Your goal is to fill the remaining empty cells. The rules are strict. Each row must contain numbers 1 to 9 exactly once. Each column must also contain numbers 1 to 9 exactly once. And finally, each of the 9 3 by 3 subgrids must contain numbers 1 to 9 exactly once. No number can repeat in any row, column, or 3 by 3 block. Sounds tricky, right? That's where backtracking comes in. Backtracking is a general algorithm for finding all, or some, solutions to computational problems. It incrementally builds candidates to the solutions. If a candidate doesn't meet the problem's constraints, it backtracks or abandons that candidate. Think of it like navigating a maze. You try one path. If it leads to a dead end, you don't keep going deeper into the dead end. Instead, you turn around, go back to the last decision point, and try a different path. This is the essence of backtracking. Now, let's see how this applies to our Sudoku solver code. First, our program needs to find an empty cell on the Sudoku board. This is our current decision point. Once an empty cell is found, we try placing numbers from 1 to 9 into it, one by one. For each number we try, we must first check if it's valid. A number is valid if placing it in that cell doesn't violate any Sudoku rules. That means it must not already exist in the same row, the same column, or the same 3 by 3 subgrid. If the number is valid, we tentatively place it into the cell. This is like choosing a path in our maze. After placing a valid number, we then recursively call our Sudoku solving function again. This call will try to solve the rest of the board, starting from the next empty cell. If that recursive call successfully solves the rest of the board, meaning it finds a valid number for every subsequent empty cell, then we know our current choice was correct. The puzzle is solved, and we can stop. However, if that recursive call fails, meaning it hit a dead end further down the line and couldn't find a valid number for a subsequent cell, then our current choice of number for this cell was incorrect. This is where the backtracking part truly shines. We must undo our last move. We remove the number we just placed from the current cell. Then, we go back to our loop and try the next number, if any remain, from 1 to 9 for this same empty cell. We repeat this process. If we try all numbers from 1 to 9 for a specific empty cell and none of them lead to a solution, it means that the number we placed in the previous cell was wrong. So, our function returns false or unsolved to the previous recursive call, effectively telling it to backtrack and try a different number there. This process continues until either the board is completely filled with valid numbers, solution found, or we run out of options, indicating no solution exists for the given puzzle. In our code, this would involve a main solve function, a helper find_empty function to locate the next blank space, and an is_valid function to check the Sudoku rules for a potential number. The solve function would then loop through numbers, make the recursive call, and crucially, reset the cell if the recursive call doesn't lead to a solution. It's an elegant and efficient way to explore all possibilities without getting stuck. Thank you for joining me on this exploration of Sudoku and backtracking. I hope this explanation has given you a clearer understanding of this powerful algorithm. If you found this helpful, please give this video a thumbs up. Your feedback is always welcome in the comments below, and don't forget to subscribe for more insights into programming and problem solving.